Today we'll be taking a look at reflection for optics for AP Physics 2. So a couple of vocab terms, wave fronts. If you think of an ocean with waves coming in, there are wave fronts, those crests that you see. So the distance between those wave fronts would be equal to the wavelength, which is lambda. You can see in the image that there's like a pulsating sphere that's emitting light. It has wave fronts. The distance between the wave fronts is lambda. Rays are essentially arrows that we draw, lines. They look like vectors that point outward from the source. They're perpendicular to wave fronts. They point in the direction of a wave's velocity. We don't have to draw wave fronts, but we do draw a lot of rays for AP Physics 2. So waves whose fronts are flat surfaces are called plane waves. So flat waves, rays for a plane wave are parallel to each other. They have to be perpendicular to the wave, so then they end up being parallel to each other. When we say light rays, we mean narrow beams of light, similar to what you would see with a laser. Okay, so getting to reflection. Most objects reflect some of the light hitting them. Some objects reflect more light than others, but most objects reflect at least some of the light. So when you have an incident ray, which is the same as incoming, if that's easier to remember. So you have your incoming or your incident ray, it's going to hit this mirror. Some of that will be reflected. So that is our reflected ray there. We have this angle of incidence, theta sub I, which is the angle the incident ray makes with respect to the normal, which is something you have to be careful with when you're looking at problems. Imagine a perpendicular line hitting the mirror. We care about the angle between that normal line and the ray. We don't care about this angle here between the mirror and the actual ray. The angle of reflection then is the angle the reflected ray makes with that normal. So then that brings us to the law of reflections, which essentially says that the incident ray and the reflected ray have to be equal to each other in terms of their angle. So our angle of reflection, theta r, has to equal our angle of incidence, theta sub I. Types of reflections. So for this class, we're looking at specular reflection. So that's when your rays strike a smooth, plane surface and the reflected rays are parallel to each other. This is simple compared to the diffuse reflection, which happens a lot in real life, obviously, but that is when parallel rays strike a surface that's not perfectly smooth, and those rays are reflected in various directions. So when you look into a plane mirror, so remember, plane mirror means a flat mirror. So let's say you have a mirror hanging in your house. You can actually pause the video after this and go try this on your own. There are 4 properties of your image when you're standing in front of a plane mirror. So first, your image is upright. So if you are standing up, your image is also standing up. If you are upside down, your image is also upside down. It matches your orientation. The image is the same size as you. This is something that a lot of students and just people in general struggle with. I did post on Google Classroom. There's a Vsauce video about a spherical mirror, and in it he does this quick little demo where he traces out the area of his phone, the shape of his phone on his bathroom mirror with soap, and then he pulls his phone farther and farther from the mirror, and you can see that it's still matching the size that he had traced out on the mirror. It's pretty interesting. Which brings us to our third point, that the image is located as far behind the mirror as you are in front of it. So if you're standing a meter away from the mirror, your image is a meter into the mirror. And also your image is reversed, which I think we all know. There's just a picture there of an ambulance, how they write it backwards, the word, so that if you're looking in your review mirror in your car, you can see that it says ambulance, since the image will be reversed. So 4 properties when you are looking into a plane mirror. So talking about reflection then with plane mirrors, rays reflect from the mirror and hit the eye, but to our eye, it looks like the ray is originating behind the mirror. So this is why an image appears to originate from behind a plane mirror. It looks like there are images behind the mirror, inside of the mirror. And because none of the light rays actually, there's no flashlight or anything actually inside of the mirror creating these rays, that the images are called virtual images. So this is our virtual image We have light that is bouncing off of the object, hitting the mirror, bouncing off the mirror, hitting our eye. If we extend those rays outwards, we have our virtual image back here. And you can see that this distance from the mirror to the virtual image should be the same as the distance from the mirror to the actual object. You could use the law of reflection to actually prove that DO here, the distance from the object to the mirror, is equal to DI, the distance from the mirror to the image, because we know that our incident angle theta has to be equal to our reflected angle theta right there. And then we could use geometry to actually prove that those two distances are equal. We talked about plane mirrors, so flat mirrors. Now let's talk about spherical mirrors. And we have two types of spherical mirrors, concave and convex. So if the inside surface of the spherical mirror is polished, it's a concave mirror. So if you look at this image here, you can see that that black line is on the concave part of the mirror. So when we look at images for problem sets and things like that, the actual reflective surface is that black line. So we draw the rays hitting that black line. So we have an incoming ray and it's reflected off of that curved concave mirror. For our convex mirror, you can see that the opposite side of the mirror is reflective. So that's our convex mirror. We have some vocab for this. So if we extended this, you can see here, we're really just looking at one segment of this mirror. So C here would be the center if we actually extended that and made the whole sphere. So C is the center of curvature and R is the radius of the sphere. We also have something called the principal axis, which is our line that goes through the center of curvature, and then we usually extend it through the mirror. And we'll have some more vocab in a second as well. So the law of reflection still applies for spherical mirrors, and the normal is drawn perpendicular to the point of incidence. So my normal line is the perpendicular line where the ray actually hits the mirror, perpendicular to the mirror. And like I just said, the principal axis is a straight line drawn through the center and the midpoint of the mirror. That is very helpful as like a reference point when we're drawing pictures. And then our image point, if the rays are near the principal axis and they cross at the image point after reflection, it is a real image. So we'll get more into this, but essentially, if you're drawing your rays, I have two rays here that are drawn coming from this tree, and they actually do physically intersect. So we say that's a real image. We'll have examples where we have to extend the rays into the mirror and they virtually intersect. So we have a virtual image. But if your rays are physically intersecting, you have a real image. An object infinitely far away from the mirror on the principal axis gives rise to an image at the focal point. So that's just saying if my object is infinitely far away, as long as it's along the principal axis, our image should be created at what we call F, the focal point, and the distance between the focal point and the distance between the focal point and the middle of the mirror is called our focal length. That's a lowercase f, so our focal point is a capital F. We have this little equation. So for a concave mirror specifically, if we wanted to know what the focal length is, that is 1/2 the radius. And this only works for rays that are close to the principal axis, which essentially all of them are for this class. There is something called spherical aberration, and that's the fact that a spherical mirror does not bring all rays parallel to the principal axis to a single image point, only the ones close to it. So we are going to work with ideal situations where the rays are close to the principal axis. A couple of other things. So the focal point, capital F, of a convex mirror is actually behind the mirror. And the distance from the focal point to the midpoint is still just the focal length, lowercase f. So for a convex mirror, we have the same equation for a concave mirror for the focal length, but we have that negative sign in there since it is actually behind or into the mirror. This slide is very helpful. It has the rules for drawing our 3 rays for concave mirrors. So I would definitely jot this down in your notes. So let's say that we have an object in between the center and the focal point. So here's our object. We typically draw it as an arrow. It is upright. It's right here. Our first ray that we draw. So if our goal is to figure out where is the image, and is the image going to be inverted? Is it going to be bigger? Is it going to be smaller? And where is it going to be? We have to draw rays in order to figure out where all those answers to those questions. So really you only have to draw 2 rays, but a lot of the times it's helpful just to have the third one so that you can make sure that you are right. So for the first ray we draw it parallel to the principal axis, and then it reflects and goes through the focal point. For the second ray, you start it always at the top of the object, and it goes through the focal point and then reflects parallel to the principal axis, so the opposite of ray number 1. And then ray number 3, it follows a path through the center, so it strikes the mirror perpendicularly and then reflects back on itself and goes through the center. And where those 3 rays would intersect, that would be where your image is. So as you can see looking at this, our 3 rays have been drawn and they intersect right here. So this is considered a real image because our rays physically do intersect right there. And it is also inverted because it was flipped, and it looks like it's bigger as well. And this happens for all points on the objects. We draw the rays coming from the top of the object, and wherever our rays intersect, we say that's the top of the object, but this would be true for all points on the object. So again, this was for concave mirrors. There is something called the principle of reversibility. So if the direction of a light ray is reversed, the light retraces its original path. I honestly feel like I don't typically use that often, but if you interchange the locations of the image and the objects, you would see an image that is real, inverted, and smaller. So you could flip those and the picture would just look the same. It would be flipped though. If an object is placed between the focal point F and the mirror, the resulting image is virtual, upright, and larger than the object. So going back to this example, remember our object was between the center and the focal point, and now it's saying, okay, what if the object is actually between the focal point and the mirror? So if we go through and try to do our 3 rays, we have our parallel one that bounces off and goes through the focal point, and then we have the one that goes through the focal point and bounces off parallel. But see how this second ray really doesn't go through the focal point physically. You have to extend that. I typically draw a dashed line through the focal point and then go this way and bounce off parallel. And then we have the one that goes through the center. So you can see that sometimes 2 of the 3 rays are easier to draw than maybe one of them. But if you look on the left here, these rays the reflected rays do not intersect. So we don't have a real image. So what we have to do is extend those reflections, and where those intersect, we have our virtual image. So in this case, we have a virtual image that is bigger. So that is if the object is between the focal point and the mirror. Lastly, we have ray tracing for a convex mirror. So we have our red arrow, which is our object, and then we end up with our blue arrow that is our image. So very similar to ray tracing for concave mirrors, our first ray is parallel to the axis and then reflects through so that it looks like it originates at the focal point. So we have to extend that reflection so it goes through the focal point. So as you can see for a convex mirror, the focal point and the center appear like they are inside of the mirror. So we have to trace that one back through the focal point. The second one initially heads towards that focal point, but then bounces off parallel. So you can see that parallel part was extended there. And then the third one goes through like it's going to go through the center. So that part was extended here and then bounces off the mirror perpendicularly. So because the reflections don't physically intersect, we have to have the reflections like their extensions, their dashed lines intersect on the right here. So then we have a virtual image, which in this case is smaller and it's upright. So the three rays converge on a virtual image behind the mirror. Smaller and upright, the virtual image is always like this no matter where the object is placed. So the nice thing about convex mirrors is it doesn't matter if my object is really close to the mirror or really far away. You're always going to have a virtual image that is smaller and upright. So that's nice because compared to concave mirrors, it does depend on where the object is. So mirror magnifications, lowercase f is the focal length, d0 or d0 or do, whatever you want to call it, is the object distance, di is the image distance, and m is the magnification. And that is the ratio of the height of the image to the height of the object. So concave mirrors, these equations are the same for convex mirrors, except f is negative. So we have this little mirror equation here. So 1 over the object distance equals 1 over the image distance plus 1 over f. And then the magnification equation, so m is the height of the image divided by the height of the object, or you could say negative the image distance over the object distance. This slide is very helpful. It summarizes everything that we just talked about, so you can see that it does tell you differences for if the image is virtual. A lot of the times that means that our quantity is negative.